This assessment asks us to give the mechanism of the base catalyzed aldol on screen, making sure to show why it's catalytic or how it's catalytic in hydroxide. As we always do with these problems, I've numbered the carbons. What you'll notice is we're starting with this molecule on the left and using 2 of them to make the product on the right. So you see the numbers, the labels 1, 2, 3, 4 show up in 2 different places, 1, 2, 3, 4. And then when the second molecule is added, 1, 2, 3, 4. What this numbering shows us is that carbon 2 is going to attack another molecule's carbon 1. Carbon 1 as an aldehyde is electrophilic, so we need somehow to make carbon 2 nucleophilic. Well, good news, this hydrogen is alpha to an aldehyde, so it's an acidic proton. We can make carbon 2 nucleophilic by forming an enolate. Let's start there. So the reaction will begin with hydroxide removing the alpha proton. So the electrons adhere, form the double bond there, the new carbon-carbon double bond. The pi electrons will move up onto oxygen. That's going to give us our enolate. Now we're going to use equilibrium arrows because hydroxide is not a particularly strong base. And so most of this equilibrium is going to be shifted to the protonated aldehyde or the neutral aldehyde. We're making very little enolate in this reaction, but we're making some. And if we keep those carbon labels, we can now label 1, 2, 3, and 4. We've done what we hoped to do. We made carbon 2 nucleophilic. Well, the good news about this not fully deprotonating is we still have lots of the aldehyde left. So we can draw another molecule of the aldehyde. Let's put the numbers back in. 1, 2, 3, and 4. And now our nucleophilic carbon 2 of this molecule can attack the electrophilic carbon 1 of the aldehyde. And so these electrons can collapse, push out the pi electrons to attack carbon 1, and push the pi electrons onto oxygen. Once again, this reaction is at equilibrium, so we'll use the reversible arrows. We're going to keep this molecule, it will keep the same skeletal structure of that. We've reformed the carbon-oxygen double bond. So that's the reformed carbon-oxygen double bond. We have a bond at carbon 2 attached to the new carbon 1. So this is going to be O-. Carbon 1, which is here, is attached to 2, which is attached to 3, which is attached to the pyridine ring. So let's make sure we get that right. This is our pyridine ring. Let's put those numbers back in. Again, 1, 2, 3, and 4. 2 attacked carbon 1, 2, 3, and 4. And of course, 3 in both cases is attached to the pyridine, but we haven't drawn that. At this point, this alkoxide is going to react with water. There's still water around. And this is where we're going to see why this reaction is catalytic, because when we protonate this alkoxide, we're going to generate the product up here, still using the equilibrium arrows. But what else have we made? We've also made hydroxide. So in deprotonating water, when this alkoxide deprotonates water, we make hydroxide again and our product. So we've completed formation of this. Now, in terms of the catalysis, the reaction started with a hydroxide doing our initial deprotonation, and the reaction finishes by producing hydroxide again. We use it to start, we produce it in the end. The reaction is faster because we have hydroxide present. We see why hydroxide is the catalyst for this reaction and our mechanism.